Okay, I'm going to jump right in here and get right to work. This is page 283. Thanks, Austin. Page 283 in the textbook, if you're following along there. And we will determine the impulse from the area under a force versus time graph, including both positive and negative force, and uniformly change the force. I can cover this in 3 minutes if I have to. I won't, but it's that simple. Okay? Have we done area underneath the graph type thing before? Yeah, you did in grade 11 a velocity time graph. Have we done it in grade 12 already? Maybe, yeah. So this might be the first time you've seen it in grade 12. But I will tell you, you're going to see it more than once in grade 12. Okay, so some general theory. I would not really worry about writing any of this down. Just sit back, enjoy, soak it all up. If a constant force acts over time, the basic graph will look like this, right? If you've got a force versus time graph, and it's a constant force means the graph remains constant, and it, nice straight like that, right? And force multiplied by time would be the area under the graph, would it not? Because the area under the graph is a rectangle that has a height of force and a base or length of time. And so force times time is the area under the graph. And we know that impulse is defined as force multiplied by time, right? J equals F times T. We learned that yesterday, right? Impulse, J is equal F times T. And so therefore, the area under the graph is defined as the impulse. Now, is this only true when the force is constant?
Yes.
You're wrong, Josh. The answer is no. I think you were just saying that for added effect.
I haven't been paying attention.
Oh, you haven't been paying attention. Oh. No. In most cases, though, the force is not constant, right? And increases as colliding objects compress and decreases as they move away from each other, right? So if you imagine a tennis ball hitting a racket or a bat, I guess even a golf ball, you've seen high-speed camera of a golf ball hitting a golf club, you'll know that the golf ball compresses. And as that compression happens, the force increases, right? And eventually when that ball is completely compressed, then it starts to expand again, and the force actually decreases. And so you get a graph this is a little bit simplified, right? But generally, in the compression phase, the force increases to some maximum, and then it rebounds, and the force actually decreases. And so you get this triangle type phase, right? But again, the area under the graph is equal to the impulse. Okay? So in this case here, do I have it or do I have to write it? I have to write it. Do you guys have this picture at all?
Yeah.
You do somewhere? I think you do, right? Okay, awesome. Okay, so you can just sort of make notes on the side there, I guess, if you want. Have you got it? I'll pause for a second. Okay, so in this case here, the area would be the triangle. It would be 1/2 the base times the height. The base is from 0 to 1.2. And the height is 25. So 0.6 times 25. 0.6 is 3/5. 3/5 of 25, I think is am I right? 15? Can someone do that for me? Yeah, I did it right in my head. 15 what? What's the unit? What's the unit for impulse? Force multiplied by time? Newton seconds. Newton seconds. You put a little dot in between. You don't have to, or you can just, but it's not newtons per second. That means divide by. It's a Newton second. 15 Newton seconds of impulse. If the golf ball compresses more and can expand that time, you get a greater amount of time that the force is on there, the ball will go farther, right? That's why they want balls that compress more to a certain degree. Any questions about that? Basically, you're just finding area, right? Okay. Here's another example. Determine the impulse for each of the given graphs. So in this case here, we have a stretched elastic band. It applies more force than a limp elastic band. The applied force is decreasing over time as the stretched band returns to its relaxed state. So sometimes you might not have the force going all the way down there. What do? Break it into a rectangle and a triangle. So it would be base times height divided by 2 plus base times height. That would be base of 1, height of 20 divided by 2, which is 10, right? 1 times 20 divided by 2, or 10. And the triangle, the base again is 1, and the height is from 20 to 70. Don't just make it 70, right? The height of the triangle is from 20 to 70, which of course is 50. Oh, and I have screwed up royally, haven't I? Yeah, so what did I do wrong here? I divided this one by 2, and I shouldn't have, right? This is the one that should be divided by 2. Yeah, I probably did that on purpose. That's going to be 20. This is going to be 25. 45 Newton seconds. And remember, too, down the road here, that impulse J is equal to the change in momentum, which is mass times delta V. And because you can't change the mass of the ball, the object that's being applied to a force, that makes the change of velocity greater, which makes it go faster and go farther. What do you do if it's like this? This is non-uniform changing force, right? The force is not changing uniformly. It's kind of increasing and then it's going like this. This is in fact a normal curve, a normal distribution curve, which I don't think they teach much anymore in applied math. What would you do? Well, you'd have to solve it by estimating and counting. You'd have to remember doing this. Remember counting squares in grade 11 at the very start there? Remember that? So you'd have to actually count squares, or you'd have to learn calculus, find the equation for that curve, and then do integration. You won't have to do that. You are only responsible for ones that look like this, or that, or that. Not those exact shapes, but basically triangles and rectangles.
Yay.
Okay, so there are some textbook questions. You might want to jot those down on that page. I think what I've done is I've provided the actual graphs for you on that sheet so that you're not marking up the textbooks and you don't need the textbooks with you kind of thing, right? So all you have to do is find the area. And of course, unfortunately, the answers are in the book. I guess I could have put the answers on that page, but I hadn't thought of that until just now. So that's day 1.
Day 2.